Okay, so welcome to week 5 here. There are 2 topics that I want to talk briefly about. Normal forces and contact forces can be a little tricky. Okay, being able to figure them out is going to be one of the keys to trying to understand the physics that's going on. So I want to make a distinction between 2 of these contact forces. So let's do an example. I have a mass sitting on a table, mass M, and what I'm going to imagine is that there is some force, an external force, other than the contact, other than the normal force of the table. I've got a table here. But there's another force. I'm going to push down with some force F. That force acts at some angle theta. When we think about contact forces, you want to think about 1, normal forces. Okay? So if I draw a free body diagram, on the mass, I do have gravity acting downward. And I have this contact force N acting normal to the surface, hence normal force. But the contact force need not be normal. And in fact, in this case, I've drawn it explicitly not. So if I draw this force here, this applied force, it acts at some angle theta to the horizontal. Okay? So when you're doing these problems, keep your eye out for those. Also, don't forget to think about Newton's third law. One of the things that's going to help you deal with problems that have multiple objects is to remember that Newton's third law of pair forces act on different objects. They act on different objects. So a Newton's third law pair force, or a pair of them, don't act on the same object. So while there's a force from the table acting upward, call that N, acting upward on the mass, there's an equal and opposite force acting on the table downward. So don't forget this. The other topic that's a little tricky are pulleys and ropes, So one of the things that you want to keep in mind is that you assume, so for a rope, we're going to work with ideal ropes. That is, the mass of the rope is 0. That means that the acceleration really can be arbitrary. That is, there's no inertia for the rope. So it responds instantly, it doesn't bow, and so we'll deal with those sorts of things. The other thing that's important about a rope is that it only pulls. Okay? So in this slide, here's an example of a rope pulling on a box. And if you look at the free body diagram on the box, you'll note the weight, the normal force, and you'll notice that the tension is pulling on the box. Now in this slide, you'll also see a free body diagram done on the rope. That's fine. But just know that when you're dealing with ropes, ropes pull, and they're massless. Now you're going to see a lot of examples with pulleys. Now again, we're going to idealize the pulley. We're going to assume that the pulley has no mass, no friction, and so it can respond instantly as well. So when you think about a pulley, imagine, I always think about a circle. There's this axle here. Okay, and so it spins about the axle. And so maybe I have a rope that goes over the pulley like this, and maybe I have 2 different masses, M1 and M2. All right. When you think about breaking this problem down, don't forget, you might want to draw a free body diagram for both objects. That is, if I want to do a free body diagram with mass 1, it looks like this. Let me put 2 different coordinate systems on here. I'll put this Y1, and I'll call this Y2. You may want to think about that, about why I would do that. This one would have M1G acting downward, and a tension acting upward. And the key thing here, because the ropes are massless, if I draw a free body diagram on mass 2, again, I have gravity, M2G, acting downward. I'll also have the same tension acting upward. So the pulley doesn't affect the value of the tension. So in this slide here, you see, a slightly different configuration. We make an explicit point here that the tension in the massless spring is unchanged by passing it over this pulley. And we'll assume that this is the case for all pulleys. Now, if you don't like that idealization, just think about the pulley as being really, really light, made of plastic, and the ropes are really, really beefy. Or another way to think about this, if you want to take the mass or the masslessness of the rope into consideration, think about really heavy objects, really massive objects, compared to really, really thin strings and really, really light pulleys. Okay. So in this particular case, what you may do is you might imagine doing two different free body diagrams, one on mass A, one on mass B, and keep your coordinate systems straight. I would do the example on slide 70. I think that's a really good one. When you assign your coordinate systems here, if you may not have guessed yet, the reason why I chose the coordinate systems this way is that when mass 1 goes up, y1 increases. But I want that to coincide with y2 increasing as well, so I choose y2 to be down. If I didn't do that, then when y1 increased, y2 would have to decrease. If mass 1 accelerated positively, y2 would have to accelerate negatively. Think about that. I chose the coordinate system so that when m1, if it accelerates in a positive way, m2 also accelerates in a positive fashion. Think about that a little bit, but as always, come and chat with me if you run into problems.